Today we're going to take a look at section 211. It's a continuation, if you will, from what we did last time. Last time we looked at the Cartesian coordinate system, and in particular we looked at graphing lines. And what we're going to be focusing on in this section is graphing things that aren't lines. That's what we're going to be moving into. So let's actually start with something that looks quite similar to what we did in the last section. We're going to find the x and y intercepts, though, this time specifically, and use them to graph the line. Now, what we learned in 210 is that you can use any 2 points to actually graph the line. It doesn't have to be specific points. But if it's asking you to find the intercepts anyways, those might as well be the points you use, and you might as well not find any others. So finding the x-intercept, if you'll remember, is letting the y equal 0. So we have 2x minus 0 equals 4. 2x equals 4. And if we divide by 2, we find out that x is equal to 2. Okay, so that would be my x-intercept. And that would actually mean that the x value is 2 and the y value is 0. Remember, intercepts are points, ordered pairs. So 2, 0 would be the point right here. Okay, everybody good so far? Fabulous. And then we want our y-intercept. So our y-intercept is when x is equal to 0. So we're going to do this one with 2 times 0 minus y equals 4. Well, 2 times 0 is 0. So I have 0 minus y, or just negative y equals 4. And then I would need to get rid of that negative. So you can either say you're going to divide or multiply by a negative 1. And then your y value is negative 4. So again, the ordered pair is x equals 0, y is equal to negative 4. And if we plot that one, it would be down here. And then just as we were talking about on the homework, we connect the dots. And draw our arrows on the end.
I kind of just drew my line until I hit that.
That's fine, you can. The arrows on the end indicate that it continues on forever. If you draw it off of the foreseeable screen, if you will, then you're doing the same sort of thing.
Okay.
So, yeah. There are some classes I would teach that would be a little more persnickety about your little arrows, but it's not a big deal. Okay. All right, all good? It's not really any different than last time, except that we're being very specific because it asked us for x and y intercepts anyway, so we used those to graph it. So let's actually take a look at another one. This says the graph of the function is given below. Clearly it isn't drawn in there. I'm going to draw it for you. It would be drawn in there if you were doing it on your homework. So this is how it would have shown up to start with. Let me make sure I get it right. All right, so pretend this is how your question started, okay? It said, given the graph below, and it starts out looking like this. So it looks like a V. The question, it simply asks you to find the x and the y intercepts. So we're going to do the same thing that we did on the last one. We just don't have an equation from which to look at. We're looking at a graph instead. And it's not a line this time. That's okay. All of the qualifications still apply. We still find the x and the y intercepts in the same way. So if we're looking for the x-intercept, it's where it crosses the x-axis, so it's the same as where y equals 0, or you can think of it visually as crosses the x-axis. And there's actually 2 locations where that happens here. Where does it cross the x-axis? At what x values? Yeah, at negative 4 right here, and at 0. So there are 2 x-intercepts. One is at negative 4, and then y is 0, and the other one is at 0, and y is 0. So there's 2 of them this time. That doesn't happen with lines. With lines, there's only 1. But with other graphs, there can be more than 1. And then the y-intercept, of course, is where x is equal to 0, or where it crosses the y-axis. And that actually is a point I already listed, right? It crosses the y-axis also at the origin, 0, 0. So I don't actually end up with any additional points of interest, if you will. I just have the same point of interest because the x and the y happen to have one in common where they cross because they're crossing at the origin. Now, you could have multiple x-intercepts. It's possible to have multiple y-intercepts depending on what kind of a graph you're looking at. So do be careful to not just give one answer and then call it good. Make sure that there's not more than one. Anya?
I have a question. It's just because I'm looking at the homework and it's very similar to this.
Yep.
So like there's like a little point at the top.
Yeah.
But it doesn't necessarily intercept the line, and more so it just like sits on it.
Yeah, so there's a couple options. That's a good question. So what happens if you have other graphs? Like, let me just do the same V shape, but actually draw something different. Let's say it did this. So if it did something like that, it could have no x-intercept. Like, that's a possibility, right? And this line would continue over here, so pretend for the moment. So it could have a y-intercept and no x-intercepts. That's a possibility. Another possibility, which may have been what you were describing, is where it looks like it just touches the line and bounces off like that.
Yeah.
That's still an x-intercept. It doesn't necessarily have to cross. It still has the correct y-coordinate, which is y equals 0. So it would still count as an x-intercept. So in this case, the way I drew it, it would be at 6. So it would be 6, 0. Does that make sense?
Yeah.
Yeah, so most of them, well, I don't want to say most of them. They don't have to look exactly like this one, right? They don't have to cut all the way through. They have a lot of other options when we're considering them. Lines are a little bit nicer to work with because they're more uniform. Right, I have one x-intercept, I have one y-intercept. Unless I'm talking about a vertical or horizontal line, those are sort of unique. But otherwise, that's what it looks like. And so these graphs are going to be more varied in their appearance. We're still going to find some more x and y intercepts, but we're going to do them now for some other kinds of equations. So these actually are equations, much like the first example that we did. But it doesn't ask us to graph them. We'll get to the graphing here in a moment for some of these. But the process is much like what I did on the first problem. X-intercept is when y equals 0, y-intercept is when x equals 0. So we're going to use the equations that are given and do the same thing. So we'll do, I tend to use alphabetical order, so we'll do x-intercept first. So x-intercept is when y equals 0. So this would be 0 squared plus x minus 16 equals 0. Obviously, 0 squared is nothing. And then if I'm solving for x, I'd move my 16 to the other side. Is that green okay, or is that hard to read? It's green, all right? Okay, I could use maybe even a darker green. I don't know why. I thought OBU green today would be good. I'll make that a little bit bigger too. So add the 16. So I'm going to have x. These are going to add to 0. So I'm going to have x on the left and 16 on the right. So my x-intercept is actually 16, 0. Is that good? All right, so that's x. Now we're going to do y. So my y-intercept is when x equals 0. So now I have y squared plus 0 minus 16 equals 0. The goal is to solve for y. So the plus 0 is rather irrelevant because it adds nothing to the equation literally. And then I would add my 16 to both sides just like I did a moment ago. Difference, of course, though, is that I have y squared on the left instead of just y. So what would I have to do to solve for y?
Square root.
Yep, I need to square root it. And can you remember, there's something very specific that we have to remember when we take square roots. You have to put a plus or minus in front. Okay? What is the square root of 16? 4. Yeah, it's 4. Sorry, it's really hard to hear you guys sometimes. Appreciate it. I know. 4. And so why is that? Why do I need the plus or the minus 4? Well, because 4 times 4 is 16, right? Right, that's 4 squared. But it's also true that negative 4 times negative 4 is also 16, isn't it? So that's what happens when I take square roots, is that I get positives or negatives because negatives cancel out when they end up multiplying by each other. So I end up getting 2 answers. So over here, my y-intercepts, I actually get 2 values. I get 0, 4, and I get 0, negative 4.
I have a question.
Mm-hmm.
Do you have to write like 0, comma 4, or do you, so you have to write it down?
We do, and the reason that we need to write them as an ordered pair is because if you leave, I'll use my x as an example. If you leave something written like this, x equals 16 would actually be the equation of a line. And I don't want to represent the intercept as the equation of a line. I want to represent it as a pair, ordered pair point. So we will always write points as ordered pairs. Yeah. Good question. We mentioned it, but it's been 5 days. So it's been a long time since we talked about that part. All right, so we actually have an x-intercept 1 and y-intercepts 2 on this one. Whereas on the last one I had 2 and 1 the other direction. 4 is a little more challenging because I've got fractions involved. So the process is still the same. It doesn't matter what I'm given in terms of an equation. It's just sometimes the process is messier depending on the equation. So the x-intercept is when y equals 0, and on this one that would look like this. Right? 0 on the left. Now, what you would like to remember is the 0 is the same as 0 over 1, and why does it matter is because then I can cross multiply, and notice that when I multiply the 0 right here by the 5 plus x squared here, I still get 0. Yeah, it's really nice. So what ends up happening is that I end up eliminating the denominator because of my cross multiplication. So that part's actually fairly friendly. So I still end up with 0 on the left, and now I have 1 minus x squared on the right. So it simplifies real quick. I'm still trying to solve this for x. So because x squared is negative over here, I'm going to actually move it instead of moving my 1. Because I eventually want my x squared to be positive anyway. So here now I have x squared equal 1. So what will I do? What was that?
Don't you still root it?
I'm sorry, one more time, Anya.
Do you still root it?
Yes, you do still take a square root of it. Exactly. So we're going to take the square root of both sides. And whenever I take a square root, I need to remember a what? Plus or minus, right. And what is the square root of 1? It's 1. So I have two x-intercepts. I have 1, 0, and I have negative 1, 0. Okay, so I take each of the values I found for x, and I correspondingly, attach them to the y equals 0, because y is equal to 0 at every x-intercept. So then we're going to do our y-intercept. So the y-intercept is when x is equal to 0. So I have y equals 1 minus 0 squared over 5 plus 0 squared. So what will that give me on top? 1. And on bottom? 5. So while the values don't necessarily end up looking nice when we're dealing with rational functions like this, finding y-intercepts is usually the easier one to do. There's less work involved because the y is already solved for it alone on the left, and the right-hand side simplifies and collapses very quickly. So I end up with 0 for x and 1/5 for y. So that's my y-intercept on this one.
If we were able to simplify it, would we have to do that?
Yeah,
Okay.
like let's say that instead at the end of leaving you with 1/5, it left you with 2/4 or something like that. Yes, you would reduce.
Okay.
Absolutely. Okay, any questions before we move into some graphing stuff? Okay, we focused a lot on graphing in the last section, and specifically graphing lines. What we're going to do now is we're going to graph non-lines. Yep, you bet. Okay, graphing non-lines. So when a graph is not a line, we need more points to plot. So lines were great because 2 points gives you the whole picture of the line. 2 points, connect them, you're good to go. Doesn't work that nicely for anything that's not a line. We need more points. And in particular, we're going to say that we need at least 5. That's what we're going to go with, at least 5. If you feel like 5 still doesn't give you a very good picture and you want to do more, then that's fabulous. Oftentimes 5's enough though, so we're going to go with at least 5. And it says the numbers -2, -1, 0, 1, and 2 are often good choices. And this should say good choices for x, by the way. So you might be like, well, that's sort of vague. Like they're often good choices. When are they good and when are they not good? And I hope that with the examples that I'm doing, you'll get a sense for what that means and when maybe they are good and when they're not good. So we're going to try some examples of some non-lines. These are equations that you've seen, equations like them before. We've dealt with some of them this semester. You've certainly dealt with some of them back in high school. And you may or may not already have sort of a visual picture in your mind of what they look like. If you do, that's great. You're also welcome to confirm what we're doing when you know how to use your calculator. If you have a graphing calculator, to do that too. That's fine. But you're going to have to justify for me the 5 points. So just like when we were doing the graphing with the lines and we found 2 ordered pairs, you're going to write down all 5 of those ordered pairs. And usually in an XY ordered chart is a good way to do that. So here's our first equation. This is y equals 3 absolute value of x. So we're going to start out with this whole idea that often it's very nice to pick -2, -1, 0, 1, and 2. And I will identify for you when it comes up, because it does here pretty quickly, a place where it might not be the best choice or maybe not the cleanest choice. But in many cases, these are reasonable values to pick. So here's x and here's y. All right, so I'm going to actually fill them in here the way that they look, just to give us a concrete picture. I'm actually taking the -2 and I'm evaluating it in for x, right? So it says now absolute value of -2. What is the absolute value of -2? What do you guys know about absolute values? It's 2. Yeah, absolute values are just distances, so they're never negative. They're always the distance back to 0. So if you think about a number line and being at -2 on the number line, which would be like right here, you are 2 away from 0, okay? So this x being -2, and then I take the absolute value, is going to give me a +2, like Lindsay said. And then that 2 gets multiplied by the 3 in the front to give me what? 6, exactly. Okay, so we're going to try that now with -1. So we have 3, absolute value -1. Okay, so again, we're working from the inside out. So what's the absolute value of -1? 1 times the 3 in front would give me a 3. Now we're going to do 3 times the absolute value of 0. Well, the absolute value of 0 is just 0. All right, there is no distance from 0 to itself. It's a 0 distance. And then 3 times 0 would be 0. Positives are friendlier because they are their own absolute value, because their distances equal their value. So the absolute value of 1 is 1, and 3 times 1 is 3. And then we'll do 3 times the absolute value of 2. So the absolute value of 2 is 2 times my 3 would be 6. Okay, so I wrote a lot of work out here on this particular problem. What do you really need to show me? Well, you need to show me these ordered pairs or whatever other ordered pairs you might pick. And you need to show me the y values that go with those x's. Okay, so do you have to show the part in between? No, so if you want to use your calculator or you want to use a scratch paper, that's fine. It kind of looks a little bit messy, I know, to write it all the way that I did. I understand that. But those parts that are highlighted in yellow, those are the important pieces I need to see. What we're going to do next is we're going to actually graph those points. So we're going to graph -2, 6, which would be about right here, -1, 3, 0, 0, 1, 3, and 2, 6. What shape is this going to create? A V. This one will actually be a V. We're going to get the U shape here in a minute as well, but this one's actually a V. And the reason it's a V is because both sides are actually creating lines. They have the same slope. It's up 3/1, down 3/1, depending on which side you're on. So this is the equation that we would have been graphing. Now, if you didn't want to pick -2 and -1 and 0, 1, and 2, is that possible? Sure it is. It's really nice to at least pick something on either side of 0. It's a really smart thing to do. That way, hopefully, you can get the sense of what's happening both when numbers are positive and when numbers are negative. It's kind of nice that you pick the same x values, positives and negatives, right? So +1 and -1, because it's an absolute value. It kind of gives a sense of symmetry that's going on here, and we'll talk more about that symmetry in a moment. So let's do the same thing again, but now we're going to do the graph of y equals -x². So again, it's kind of nice to pick those same ordered pair point, or those same x value points. So I'm going to do that, -2, -1, 0, 1, and 2. And I'm going to go ahead and write the work out right on the table just like I did last time. If you don't want to write it on your table and you want to do it in scratch work on the side or something, that's fine too. But I have a negative here, and then I have -2². So again, we start on the inside. I have a -2, and that -2 is squared. So what is the -2 squared? 4, exactly, and it's +4. And then I have the negative out in front that will change it into a -4. So I end up getting a -4 because of the negative at the very front, not because of the negative on the inside. Then we're going to do the opposite or negative of -1 squared. So again, -1 squared is 1. And then the negative out in front makes it a -1. 0. Oh, 0 is our good friend. Because 0 squared is 0. And the opposite of 0 is still 0. He is his own opposite. Now I have -1 squared. Well, 1 squared is 1. And then the negative in front still makes it a -1. And then I have the opposite of 2 squared. And 2 squared is 4, with the negative in front making it a -4. Okay, any question about where any of those values came from before we plot them? All right, so we are going to plot them. So we have -2, -4, -1, -1, 0, 0, 1, -1, and 2, -4. Now it's kind of tempting to think that this might look like a V, but it actually doesn't, and let me show you why. If you were to consider these points that are sort of tucked in here really tight around the origin, you would go down 1 and left 1 or down 1 and right 1, right? Does that make sense? But if you take each of those ordered pairs, so let's just take 1, 1 actually. If I were to get over to 2, I would actually have to go down 3 and over 1. The ratio is different. That didn't happen on the last one. The last one's ratio is down 3 over 1, down 3 over 1, or up 3 over 1, up 3 over 1. This changes. It went down 1 over 1, and now it's going down 3 over 1. So this is not a V shape. This is actually a parabola. It's a U shape. So it ends up looking like this, roughly speaking. Okay? So what you can know right now then is that anytime you have absolute values, they look like these. And anytime you have x² graphs, they look like U's. Okay, so that's a good rule of thumb to remember as you're connecting the dots so that you don't have to be so careful at do my ratios match or do they not match on each of them. All right, we're going to change it up just a little bit. Very similar equation, number 7 to number 6. What's different? Yeah, the +5 on the end, right? So now I actually have to add 5 to the ending values. This is -2, -1, 0, 1, and 2. And we could actually take all the ordered pairs that we got from the last equation that we did, and then we just add 5 to them. So I'll write them all out just because it won't always work out that way, that successive problems, have that, nice feature to them. But we are going to do this work on each of our problems. We're going to take, in this case, negative 2 squared, which we said was 4, times the negative 1 at the beginning, which would be negative 4, plus my 5, which would be 1. It should be 5 more than the previous problem that we had. And then we have negative of negative 1 squared. So negative 1 squared is 1, times the negative in front is a negative 1. And negative 1 plus 5 is 4. 0's so nice. 0 squared 0 times negative is still 0, plus my 5 is 5. Then we have a negative 1 squared plus 5. And the pattern has to reverse itself just like it did over here, right? It goes back down to the same value that it was before because of the symmetry of our relationship in our graph. So this is going to go back down to 4. And then the other one, whoops, has to go back down to a 1. So there's lots of ways to sort of piece that together, but you will have all the same ordered pairs on the right-hand side, just plus 5 from the last set of ordered pairs that we did. And we'll plot them. So we had negative 2, 1. I have negative 1, 4, 0, 5, 1, 4, and 2, 1. And again, we talked about the fact that this is a U shape. So it looks something like that. What it should look like is that we just picked up the graph and we just moved it up 5, right? That's what it should look like, because that's what we literally did. And that's actually a college algebra concept. So those of you who maybe are taking college algebra next semester, you'll get into that idea of taking graphs and moving them around without actually changing anything except for their placement on the ordered axis, right? So this is what's going on this graph. Now, 8's a little more interesting. The reason that 8's interesting is because I have a fraction involved, to be honest. The cubes also makes it a little interesting, but the fraction involved makes it kind of weird. On this one, it happens to still work out really nicely to pick values that are negative 2, negative 1, 0, 1, and 2. But it certainly seems like maybe, picking a value of negative 1's not so nice. The problem is that the values that are nice get really big off my graph so that it's hard to plot them. So that's something else that you have to keep in mind, is I still have to have values small enough to plot. For example, it'd be really nice to cancel that 4 out in the denominator, right? Absolutely. And the number 2, x equals 2, will do that. Well, so will the number x equal 4. So give us just a moment without writing it into your table, and let's just see what happens, though, when I put in the number 4. So if I put in the number 4, what's 4 cubed? Do you know? Bigger. 64. Yeah, it's 64. 64 will, in fact, reduce with the 3/4, right? Because it's got a 4 in it. And it'll reduce to giving me a 16. That's what it will be. And then 3 times 16 is, do you know that one? 48. It's a nice number. There's nothing wrong with it except that my graph doesn't go out to 48. Agreed? So for that reason alone, it ends up being not a very good number to pick, even though I end up with a nice whole number value, because it's not on my graph. So if that happens, then you're kind of back at the point where you're like, okay, well, that kind of didn't work. So maybe I should go back and try that negative 2, negative 1, 0, 1, and 2. Even though the number was nicer, I don't have a fraction involved, it's not on my graph. Now, negative 2 actually works really well, so it's not a bad number to pick anyway. It's the negative 1 and the positive 1 that are kind of ugly. So if I have 3/4 times negative 2 cubed. So what is negative 2 cubed? What's 2 cubed? 2 times 2 times 2. 8. Yep. And since I have 3 of them, right, they're all 3 negative, I'm going to end up with negative 8. Does that make sense to everyone? Okay, so this ends up being 3 over 4 times negative 8. I am running out of space. Let me move this over. The negative 8 and the 4 will reduce, right? To a what? Negative 2. So then I have negative 2 times my 3 for a negative 6. Again, if that's too much commotion inside of your table, just do it as scratch work on the side. It is negative 6. Negative 1. Well, in some sense it's nice because cubing the number 1 is easy, right? I mean, 1 times 1 times 1 is just 1. It's negative 1 because I've got a negative 1 times negative 1 times negative 1. The part that makes it kind of ugly is that this is negative 3/4, which means plotting it's going to be a little bit inaccurate. I mean, we're already going to be a little bit inaccurate every time we plot points, but this one's going to be even more so because it's not at a whole number value. But we're going to have to kind of deal with it because it doesn't get any better because I'm off my graph if I make the value of 4, like x equal 4. X equals 0 is lovely because what happens when I do 0 cubed times 3/4? Yeah, we get 0. So 0 is fabulous. And 1 and 2 also have some of the same things going on that they did for negative 1 and negative 2. We have 1 cubed is 1, right? I don't have to worry about negatives anymore. And 1 times 3/4 is 3/4. And then the same thing when I do the other one here at 2. 2 cubed, here's 3/4. 2 cubed is 8, just like I had that negative 8 before. And the 4 and the 8 reduce to a 2. So I have the same 6, just as positive this time instead of negative. So my values have this sort of cyclic or repeatingness to them, symmetry to them. They just end up being positives instead of negatives. So over here on my graph, I had negative 2, negative 6. I have negative 1, negative 3/4. So that's not absolutely awesome, but you know, we're going to do the best we can. I have 0, 0. I have 1 3/4, and then I have 2 6. You've probably seen this graph before, maybe not in a while. It's not as common as like an x squared graph or maybe an absolute value graph. That's the one I was thinking of. But it looks like this. That was not connected well. Let me try that one more time. Okay, I'm more or less pleased with that. So it kind of looks like a squiggle. It's a very mathematical term for you today. It's a squiggle. But this is a cubic graph. Cubic graphs, they look like this. They tend to have the same sort of behavior. And sometimes you could see them again like the other graph that we had, shifted up or down or left or right or something like that as well. Okay, does that make sense? All right, the last thing that we're going to take a look at in this section, I think this is the last thing, is the symmetry part. Is that what's last? Yeah, we're going to look at some stuff with symmetry. All right, so there are 3 types of symmetry specifically that we are going to look at. We're going to look at x-axis symmetry, y-axis symmetry, and origin symmetry. There's actually another type of symmetry as well. You'll do it in college algebra. It's called, well, I guess origin covers both of them. So we'll leave it at that. I was thinking about even and odd, which were something that we do there, which is similar but a little different. All right, so symmetries. We have x-axis symmetry. It means it's a reflection of itself over the x-axis. And I'd like to just draw a sketch for you to give you a picture of something that kind of looks like that. And for lack of better terminology, it looks like a sideways parabola. A parabola that's flopped down, right? A y-axis symmetry would look like the parabola without it being flopped down, right? It would look like this. So in both of those cases, what we're basically saying is that if we took the axis that's got the symmetry, the x-axis on the first one, the y-axis on the second one. And we folded it along that side. The two images on either side would match up. Right? So your human physique has symmetry to it. It's not perfect symmetry, right? Because we all have our imperfections. But your right hand and your left hand are pretty close to mirror images, right? So if I hold my right hand and my left hand up like this, I, through the middle of my face right here, would be very much like having a y-axis symmetry. If you fold it along here, right, if I folded my arms together, they're going to match up and they're going to be the same on both sides. On the other one, the y-axis, the x-axis, I just talked about the y-axis, it's the same thing, it's just it's on the x-axis, and so you're talking about top to bottom folding over. Origin symmetry is much more interesting because it's harder to see, I think. So origin symmetry would be something like our last equation that we just did. A cubic graph has origin symmetry. So what does origin symmetry mean? Well, it means that if you were to rotate it 180 degrees, think about like a spinner on a board game, right? Like the game of life, if you've ever played that one, has a spinner. Sorry as a spinner if they do dice. But you're talking about a game that has a spinner where you're spinning it around. Think about like a roulette wheel. That's an example that we see used in casinos, right? You spin it around, and what happens is that we end up spinning 180 degrees exactly. Then we would actually have something called origin symmetry. So imagine if you took this piece that's up here at the top and you spun it around at 180 degrees, it would land on the piece at the bottom. And the same thing is true for the piece at the bottom. If it rotated around, it would land on the piece here at the top. Okay, so that's origin symmetry. Now, something very valuable to recognize is, whoops, I don't have that there. Oh, I don't have. Oh, okay. There's a note that's missing. That's okay, I'll just write it in. So note. A graph can have one of these. That's a possibility. All three of these. Or none of these. In particular, it can't have two. If you get two, you get all three. All right? So what we're going to do is we're going to go back to examples 5 through 8 above, and we're going to identify which of these types of symmetry, if any, that it has. So let's go back to 5. This graph looks like this. So I have 4 options here, right? I really have 4 options. I have x-axis symmetry, y-axis symmetry, origin symmetry, or none of these. Those are my 4 options. Do you see any symmetries on number 5? What's it look like you maybe have? Yeah, this one has y-axis symmetry. Because if I were to take the graph that looks like a V and I were to fold it along the y-axis, they'd land on each other. Or you could think about folding the left-hand side over on top of the right-hand side, right? Like if you were folding a sandwich or something like that over, right? They would land on top of each other. So yeah, this one has y-axis symmetry. It has one symmetry. How about number 6? Yeah, it's the same. This is another y-axis symmetry. Y-axis symmetry is pretty common. How about 7? Yeah, also the same. Another y-axis symmetry. And number 8, I already gave this away earlier. What's this one? Yeah, that one's the origin symmetry. So you might be thinking, okay, well, great. You only gave us examples of things that have one type of symmetry. What would it look like if it had none? Or what would it look like if it had all 3 of them? So let me give you just a couple more examples that you can draw in for when it has none and when it has all 3. And I don't have these written down, so I kind of want to make sure I'm not just doing ones from your homework. So let me look at your homework so I'm not doing the same things that they're giving you. Is there nothing? Oh, I'm not in the right place. it is. If you look at your homework, though, what you see is it's the very end of the problems. It's problems 22, 23, and 24, where they just give you pictures, and you're just identifying. So I want to give you something that they don't give you. So let me see if I can find something. Let's say that we have, oh, and I need one more. I need one to show you that's got x-axis symmetry, because I didn't do one for that either. An example of a graph that would have x-axis symmetry would be something like this. I'll start with that one. And I drew one, roughly speaking, like this before. This is x-axis symmetry. It's a parabola on its side. It would have x-axis symmetry. Notice it doesn't have y-axis symmetry, right? If I folded it over the y-axis, it wouldn't line up with anything, because half of the side doesn't have anything at all, and the other side has it all. It also doesn't have origin symmetry, because if I spun it 180 degrees, it wouldn't land back on top of itself. I'd have to go all the way around 360 before it would be back on top of itself. Something that would have none could look actually like any one of those things that we have. They're just altered. For example, let's say that the graph looked like a parabola, but it wasn't a parabola that was centered on the y-axis, right? It was shifted. Well, this doesn't have any symmetries. Not the three symmetries that we're talking about anyway, because it's shifted over. If I tried to fold it along any of my axes, it doesn't land on top of itself. If I try and spin it, it's going to turn the parabola upside down or right side up, depending on your perspective. It won't land on itself, right? So this would be none of these. Something that would be all three of these. So I'm going to draw a weird one because you've got some very standard looking ones in your homework. But one of the weird ones that this would look like is if it looked like this. I almost feel like I'm looking at a seams on a basketball, just a portion of the seams on a basketball. So hopefully you can see that if you folded it like this, your image matches over the y-axis, right? If you folded it like this, the image matches over the x-axis. So it definitely has x-axis and y-axis. And I told you before, you can't have two without having three. So if you took this and you spun it 180 degrees, it would also land back right on top of itself, making it have an origin symmetry too. So this is an example of something that would have all three. Okay? Any questions on those? Okay, let's go ahead and get started. I will tell you that for whatever reason, those symmetries really stumped my other intermediate class when they did that. So they move it a little bit fast. They move twice pace of what you guys do, because they did intermediate and college all in the same semester. It's kind of like a whirlwind craziness. But the part that surprised me the most was their struggle with the symmetry part. That's why I've spent so long here at the end on the symmetry part, is because I feel like there must have been things that I just didn't say well enough before. So be very careful with the symmetry part, because that really caused some problems in my other class, okay? So go ahead and get started, and we'll still go a little early today, but if you'll give me a good 15 minutes, then we'll head on out, and you can have a chance to look at some of these questions and ask any questions that come up.